Welcome to CS 194-15, Introduction to Parallel Programming. This semester, you're going to be learning about parallel programming, how to program machines like the Cori supercomputer that you see here in the picture, which is one of the fastest computers in the world, and it's run just up the hill at Lawrence Berkeley National Laboratory. And all of you will have access to this supercomputer for doing your homework assignments this semester. What is a parallel computer? And why do we want to use them? Well, a parallel computer is really one, and what is one that has multiple processors inside of it. And parallel computing then is using those multiple processors in parallel to solve problems more quickly than you can solve with a single processor. So let's look at a really trivial example. Let's say that we have a list of 1 billion numbers, and we want to compute the factors of those, the prime factors of each one of those numbers. And let's say that we have 1 million processors. We could give each one of those processors 1,000 of those numbers, and independently from each other, they could compute the prime factors. Now, we may run into some issues with this. These are what we call embarrassingly parallel problems. That is, they're all independent of one another, at least as I've posed the problem here. But they may run in different amounts of time. So if you had a very large number, it's going to take longer to factor that than some very small numbers. But nevertheless, this is a problem that is, in some sense, embarrassingly parallel or pleasingly parallel is what some people call it, because the problems can be solved independently of one another. Why do we study parallel program? Why would you want to take this course? Well, the first reason is because we have the need for speed. I like this picture. It's a picture of the American Magic sailboat, which is going to be competing to compete in the America's Cup this year. And this is a boat that, of course, has been designed with tremendous amounts of engineering, and it's pretty amazing in that it barely touches the water at all, as you can see. In this course, we're going to be learning how to design software that's also designed for very high performance, very high speed, and some of that will require very sophisticated engineering. So just to give you an example of some of the things that we do with parallel computing today, this one is sort of very timely. It came up earlier this year when after the breakout of COVID-19. And some researchers in Tennessee decided to look for potential drugs using computers. That is, looking for things that would be potential medical therapeutics for the COVID-19 disease by matching the molecules in known drugs to the virus itself, in particular to something called the spike protein within the virus. So they screened 8,000 different compounds, 8,000 different known drugs. The advantage of starting with known medications, known drugs, is they've already gone through an approval process, and so they're known to be safe in certain ways. And what they identified from those 8,000 was 77 of the most promising, which other people have, in some cases, gone off and done experiments on. So this is a way of using computing to quickly find interesting data sets that you might want to do experiments on. It's a very expensive computation. Another example would be, which is closer to my own research, is looking at some of the big data challenges. I work in computational genomics and using these parallel computers to do genomic analysis. It turns out that the way genome sequencers produce the output of when they read the genome is they actually produce it in little fragments. And so if you haven't ever seen that genome before, putting that together into a complete genome is very much like putting together a puzzle where you don't have the cover. Now, in this particular pieces, the 3 billion pieces are the pieces of the human genome, which we have seen before. At least there's a lot of similarity across all of our human genomes. What I work on is even more complex genomes, or things that we aren't as familiar with, at least, from things like the microbes that live in soil, that live in your body, that live all over the place in the environment. And so in that case, many of the species that live in say, a scoop of soil are things that have never been seen before. We don't even know really what the species is, much less what its genome looks like. An example also from COVID is looking at how you take the genomes from the coronavirus itself and try to understand the relationship as that virus adapts over time. There's a great website that I recommend called nextstrain.org, and they've tried to collect as much of the viral data as possible and look at the different strains. So this tree on the left is looking at the different variations over time as every time the virus reproduces, it has a chance of mutating a little bit. And so you can look at the different strains and you can see how the different outbreaks in different countries are related to one another, that you've got a certain strain that is usually dominating a particular outbreak in a particular country. That requires a very large amount of computing to map each one of those onto each other and trying to understand the similarities of the different viral genomes. So another example, I'm sure many of you are interested in machine learning. Maybe you've taken 189. I think there might have only been a couple of people who've taken that course, or others you might be interested in taking it or even planning to take it this semester. It turns out that the computation associated with machine learning has become very, very expensive. Anecdotally, I've heard that some of the engineers, the data engineers at places like Facebook that do a lot of machine learning might have 512 graphics processing units at their disposal for doing their research. And later in the semester, we'll be looking at how to use and program those kinds of graphics processing units. But here what we're looking at is over time, how much the cost of training a neural net, so the computation that precedes using that in practice, has grown over the last decade or so. So this is comparing AlexNet, which was in 2011, to AlphaGo Zero, which was the program that really trained itself in some sense to learn the game of Go. And in that time period, the amount of computing required to train those neural nets grew by a factor of 300,000. So, and these are very expensive computations. If you look closely at the y-axis, you can see that it's in petaflops per second days. That is the number of days it would take on a machine that was running this computation at a petaflop. The computer, the supercomputer that you'll be using, the Cori supercomputer, is a 30 petaflop machine. That's the hardware limit of how fast it will run. These computations, and this y-axis is really talking about observing a petaflop per second of actual performance. And as we'll see, there can be a big difference. But these are once again, it would take many years on a computer like that, even by itself. So these are very expensive computations, and we'll learn more about how we make them go and run in a reasonable amount of time on supercomputers. So what is a parallel computer in a little bit more detail? Well, there are really three main styles, and there's lots of variations on these, but the three main styles are shared memory, distributed memory, or what I'll call here HPC, or high performance computers, and single instruction multiple data, or SIMD machines. And what we'll find is things like graphics processing units will have sort of a combination of these, vector processors, as you may have heard them called, or multi-core systems. So a shared memory multiprocessor, or what's formerly called a symmetric multiprocessor, SMP, has a bunch of processors that are all connected to a shared memory. The network in this case is really just, it may be a bus. You may have learned a little bit more about this in 61C, but roughly speaking, you can think of each of these processors as being directly connected to the same memory. And that's what our multi-core chips look like today, that have multiple processors on the same chip. In a system like Cori, it actually is made out of multi-core chips, but it also has many of them put together, and those are connected by a high-speed network and those processors can then have their own memory, but they can send messages to each other in order to perform a computation. And the last kind, which we don't tend to have in very large scale today, but comes up inside of even single processors, are SIMD instructions, or SIMD operations. And in that case, what the computer is doing, it really has a single kind of control, and it's issuing a single instruction, and then that instruction is being performed on many different values at once. So for example, we can have an array of values, and we're going to add those to another array of values and do that in parallel. Well, here we'll learn a lot more about these different kinds of computers, but I just wanted to give you a sense of what these look like. Once again, this is a picture of the Cori supercomputer, and it is run basically for the science community and the Department of Energy. So these are people that are using it for things like for understanding the universe, for simulating the universe, for simulating global climate change, for simulating various fluid dynamics problems and other things. And just to give you a sense of what it looks like, so first of all, I recommend if you are interested in some of these fast supercomputers, looking at the top 500 list. It lists 500 of the fastest computers in the world, at least people that are willing to run the high performance LINPACK benchmark and put their machine on the list, but it does have some of the fastest computers in the world. Cori is no longer in the top 10, but is in the top 20 and started out in the top 10, and over time other faster computers come along, and it has, the Cori supercomputer has over 680,000 cores, each of which you can think of as of course, as a single processor, and it runs, as I mentioned before, at about 30 petaflops of peak performance. A petaflop, by the way, is 10 to the 15th floating point operations or math operations per second. So with these supercomputers, if we want to take a problem like climate change, what we do is we divide the problem domain up into pieces and give each piece to a different processor. Unlike the prime factor problem that I talked about before, those problems in climate change are not independent. If the wind blows in one region, it's going to affect the wind and the temperature in another region nearby. And so these processors have to talk to each other in the midst of the computation. Now, parallel computing is not just for large-scale supercomputing for science. It's actually hard to find parallel hardware or find any hardware chips that are not parallel today. So it's in just about everything you can find. It's in laptops, it's in server processors, and it's in graphics processors. So here's some example. The Intel Knights Landing processor has 68 cores. That's the chip that's going to be inside the Cori supercomputer that you'll be using. Cori also has some Haswell processors, which are a little bit more traditional server processors, and those have 16 cores in each node. And the AMD Risdon processor has 8 cores, at least on a chip. And the NVIDIA V100, a GPU, has hundreds of these types of cores that are a little bit simpler, much simpler, but a very large number of them. And then the fastest supercomputer in the world today is a computer in Japan called Fugaku, and that was built by Fujitsu, and this chip was designed by Fujitsu. It's based on the ARM architecture, and it has 48 cores on each one of the chips. Now, even inside of a cell phone, you'll find that there's going to be parallelism. Someone during lecture asked about whether it's an Arduino, and Arduino is actually not a parallel processor, but most of the other kinds of processors, even an embedded processor that you would see in something like a car, which you might very well have a parallel processor for that. So what are the other reasons that you might be interested in taking this course? You will certainly be learning about how to make things go fast in terms of how to write fast software, but you'll also learn about algorithms, a little bit about parallelization and what parallel algorithms look like. This is not a very theoretical course, so we'll be mostly focused on programming, but a little bit on some of the kinds of clever algorithms that come up in parallel. This one's not so sophisticated, but maybe a little bit non-trivial. So let's say that we want to add n values together. If we want to do that on a serial computer, it will take order n time, that is linear time. You just one at a time, you add them up. There's actually n-1 additions in between adding all of those up, and you can't really do it any faster than that on a serial computer. On a parallel computer, using this tree-based computational diagram, each pair of things can be added together, and you can and because you can run each one of these pieces of the tree in parallel, that is at each level, each of those levels can be run as a parallel level, that the total amount of time it takes to run it on a parallel computer is O of log n, that is logarithmic in the size of the array that you want to compute the sum of all the values of. And so that algorithm will come up over and go over and again in parallel computing. Now, I will point out that complexity is based on the assumption that we have a very large number of processors. That is, we have enough processors to basically put one at every element inside of this, inside of this tree, which is order n processors. So it's a large number, but still that algorithm is going to inspire us in things that are a little bit more practical and will take advantage of the kinds of parallel processors that we have access to. This algorithm, by the way, doesn't actually compute things in the same order as it would if you were running it in serial, where you were writing 1 plus 3 and then taking the 4 and adding it to 1 and so on. It's actually taking advantage of associativity and then is going to add up the 3 plus 2 in parallel with the 4 plus minus 6 and so on. So anyway, these are some of the things that we'll worry about when we start thinking about parallel algorithms. Now, what you saw in that example was a little bit of the difference between theory and practice, and that will be very important in this class. We're going to do a lot of work looking at the practice of parallel computing, and as I said, some work looking at the theory. I like this picture because it shows a very nice, clean picture of theory at the top, and a very messy, kind of murky looking picture of what practice looks like. And so what we'll find is that there's some very elegant algorithms, and we may use the ideas for those for practical parallel implementations, but it is also the case that in the details of the implementations, there will often be a lot of messy details. Now, trying to understand the trends in computing and in parallel computing, I think it's sort of interesting to go back and look at predictions. So this is a prediction by Thomas Watson, chairman of IBM, of course, in 1943, said, "I think there may be a world market for about 5 computers." Of course, he turned out to be quite wrong. Another similar kind of quote is from Ken Olsen, the president and founder of Digital Equipment Corporation. "There's no reason for any individual to have a computer in their home." Of course, Ken Olsen and Digital Equipment Corporation in particular went on to really create and establish the need for personal computers. Bill Gates said 640K of memory ought to be enough for anybody. Of course, the Windows operating system made it quite impossible to get by with only 648K of memory, along with many other things and applications that we use today. And finally, on parallel computing, Ken Kennedy, who's a famous researcher in parallel computing, said, "On several occasions, I've been asked whether parallel computing will soon be relegated to the trash heap reserved for promising technologies that never quite made it." Now, he wasn't the one with a tunnel vision, but all the people that were asking him this question, and even after I got to Berkeley in 1991, this question of, is parallel computing really just a niche for, say, solving large scientific problems came up. And instead, what we'll see is that, as we've seen, is that parallel computers come up all over the place. So why is it that so many of these chips today have parallel computers on them? And it's really related to Dennard scaling, which is about having, as we've put more processors, more transistors on a chip, the ability to make, so this red set of dots are the transistor counts going up over time. Notice the log scale, so exponential growth in the number of transistors per chip. But the single thread performance, the serial performance of these really started leveling off in about 2004. And the clock speeds leveled off even more around that same point in time. There was a little bit of work that was still done with some of the other features on these in the single threads that allowed a little bit more performance improvement, but basically the performance turned over in 2004. And instead what we've seen is the number of cores has increased in that since 2004, as people had more transistors and didn't know, and the best way to use them turned out to be to put multiple processing cores on a single chip. The word core, by the way, really I think came from the marketing community, because we would have called them parallel processors as we did when we were building shared memory processors with multiple chips, but then you couldn't say that your processor was getting faster. So instead they kind of coined this other phrase, processor core, and really got everybody used to using it. So that you could still say that your processor, which has multiple cores, is now getting faster each time you have a new chip out. So is this the right course for you? I've talked a little bit about what parallel programming is, a little bit about what parallel computers look like underneath the hood. And certainly we'll be programming in high performance languages, such as CUDA, which is designed for the NVIDIA's GPUs. You're going to be programming fairly close to the hardware, much more so than certainly in 61A and B, maybe a little bit closer to what you've done in 61C. The hardware and software interfaces, because you're programming so close to the hardware, will evolve over time, and so things will often change. In fact, I have to keep updating my lectures as the hardware changes. There are lots of jobs for performance programmers out there. In fact, I sometimes complain that although they've got great jobs, many of my recent PhD students are all working in some aspect of performance programming. One of them who built the genome assembly analysis tool that I mentioned earlier is now working for Intel, optimizing deep neural nets. Another one who is looking at very large-scale data analysis problems using a different kind of machine learning technique, including things like analyzing image data from the brain, is at Google, making deep neural nets run fast. And a third student who looked at problems in image analysis coming from MRI data, working with Mickey Lustig in the ECS department, is at a startup company that was recently purchased by Tesla, making deep neural nets run fast. So there's a lot of need for performance programming for some of these very computationally heavy problems, such as in machine learning. Now, there are perfectly good programming jobs and lots of programming to be done at a higher level of productivity that makes it easier to write the software in languages like Ruby, and you're familiar with Python and Java and things like that. You're much more isolated from the hardware. The interface, therefore, doesn't matter so much. The lower level interface may change, but you're all protected from it because the programming interface for your applications doesn't change. And you're looking at lots of sort of general purpose web sorts of programming applications. So, in terms of kind of the analogy to sports car, to different kinds of transportation systems, here you've got a very high-end sports car. Somebody who learns how to drive one of these maybe could also drive one of these, although they're somewhat specialized. And but you get a lot of people through a distance, very high bandwidth, if you will, as we'll talk about in a minute, on a bus. Or a lot of goods on a tractor trailer, but it's quite different than a very high performance car. So just a little bit about me, and then we'll talk a little bit more about computer architectures and so on, and performance. So I did my undergrad and grad work at MIT. I started programming in Scheme, and then I loved another language called Clue, which is very similar to Java. So definitely programming at a higher level of abstraction. The Scheme course I took was very much like 61A that you take today although it's been, of course, redone in Python. And in grad school, I started programming in parallel machines. I actually visited a place called DECSCIRC, the Digital Equipment Corporation Systems Research Center, actually here in the Bay Area in Palo Alto. And they had a little multiprocessor called Firefly. And I was looking at symbolic problems and how to map those onto parallel hardware. When I got to Berkeley, I started, one of the main courses that I taught at the undergrad level was 61B. And we used to have students write software to play games, things like that. I know you do similar things in 61B today. In my research, I've developed parallel programming languages. One's called UPC, another is Titanium, which is based on Java. UPC is based on C. And then for about 10 years, I've been mostly on leave at the lab, so continuing my research, but haven't been teaching so much, at least at the undergraduate level. I've continued to teach the parallel computing course at the graduate level with others. And I was running the supercomputing center there, which is the one that you'll be using, the NERSC Center. And these are some of the baby photos of the computers that we had over that period of time, in addition to the Cori computer that you've seen before. And worked with a lot of people trying to figure out how to map various scientific problems onto parallel computers, things like image analysis problems or looking at climate modeling problems and things like that. And today, the one project I have here is the research project that's probably my largest project is the Exabiome project that's related to this genome assembly problem and the problem of trying to analyze large-scale data sets that occur in the environment and in microbes, so microbial communities. And most recently, I've become the Associate Dean for Research of the new Division of Computing Data Science and Society. And I'm very interested in helping that organization also connect and figure out how to use computing and data science kinds of techniques broadly across the different scientific problems around the campus, that the research that people do, whether it's in science and engineering or in the humanities and elsewhere. So the first part of this class is really going to focus on performance programming even on a single processor. Why? Because if you're going to go to the trouble of making something parallel, you want to make sure you're starting with a good, efficient serial code. So this is really a review of 61C material, but when we think about writing programs at the software level, we've got variables, we've got arithmetic operations and other logical operations that we perform on them, and then control statements, so branches, loops, function calls, and things like that. And we sort of assume that every operation, a multiply and add, has the same cost. When we start doing complexity analysis, that's a typical assumption to make. So we have our little cartoon over here of a processor. It has a control piece and it's got arithmetic piece, and then there's main memory where the variables are stored. Now, of course, that's not really what happens in these computers, so we really need to think about the fact that each of our data types might have different sizes. They might be bytes or words, and they have in the address space that, and they're also, we need to read and write those into the registers because we're only going to be able to perform arithmetic operations on things that are in registers and not things that are directly live in main memory. And when it comes to control structures, the compiler then is going to translate our code in at least some obvious way into some instructions that will execute the branches, but there will be some amount of overhead in these control structures. And the hardware just executes them in the specified order. As we'll see, a lot of these assumptions are also still oversimplifications, but for now, that's what we can assume. And then the last thing, though, is that we don't worry about the cost of the reads and writes. We're only still worrying about the costs of the arithmetic and logical operations. And of course, that is still unreasonable. And so, in fact, really what we should think about is that the reads and writes are much more expensive than the other types of operations, especially the arithmetic operations. So our compilers are going to take our program written in some higher level language, in this case, something like C, and turn it into assembly language instructions that are then going to operate on that kind of abstract machine that we showed in the previous slide. So what do the compilers do? Well, they check to make sure the program is legal. They translate that into assembly code, and then they may also optimize the generated code. And so it can actually do optimizations at various points, but what we've got here on the right-hand side written in pseudocode is the assembly code. So doing a load, doing a couple of loads in addition, and then a store operation. So those all look pretty close to what you would see in the assembly language for a particular architecture. Now, what really happens, though, is that the compiler is more sophisticated about this. It does, as I said, a number of optimizations I'll talk about in a minute. But the first thing is that it actually manages the registers. So fortunately, you as the programmer do not have to think about which values are actually sitting in registers, although when it comes to performance programming, in many cases, you will want to worry about that. You will need to know exactly which variables are in registers, because those are going to be things that I can perform arithmetic operations on and are very fast, as opposed to things that have to be read from the main memory. So what the compiler does is to perform an operation called register allocation, and it decides during register allocation by looking at the program, or at least a chunk of the program, such as a loop body or a block in a control statement, or some fairly narrow region of code, what registers should be used for which variables that are in the higher level software. And it turns into actually an interesting and hard problem, which is to figure out what is the minimum number of registers and how to assign them, because some of the registers can be used for multiple variables because they don't occur at the same time. For example, in this picture, we have variables A, F, and E, and they are all being used here on the left-hand side, and that we're assuming then that and because of the way this code is written and some assumptions here about the variables not being used again, we can actually store these variables all in the same register R1. And the other variables need their own registers because they're being used, say, on two different places on the right-hand side. That's why we've got an edge in this graph. And this graph, the representation then of this piece of code, and then the analysis that's done it is a graph coloring problem where you assign colors to the vertices of the graph such that no edge connects the two vertices of the same color. That's a hard problem. It's an NP hard problem, but it is, there are heuristic versions of this that are done in, or even exact versions of it because the problems are fairly small, that are done inside of compilers. It was first done back in the 1950s. It just register allocation in general. Graph coloring then became a popular thing to put in compilers in the 1980s. I think some of the more modern compilers, such as a just-in-time compiler for Java, might use a cheaper approach because it is being run at runtime. But that just gives you an idea of the fact that the compiler is doing something non-trivial to turn your application code into something that's going to run on the computer, and you will sometimes need to worry about exactly what it's doing in terms of register assignments. And to further complicate things, the compiler will optimize your code. So this is generally great. On average, the compilers do very well at making the code run faster than before they perform the optimizations, but it's not always the case that the compiler manages to figure out what is the right thing to do. So sometimes you'll need to worry about that when you're doing performance programming. So for example, the compiler will unroll loops. As I mentioned before, there's some overhead with each of those control statements. So for example, checking to see if you're at the end of the loop. And so one of the things the compiler can do is to unroll it a certain number of times. Let's say it unrolls it 2 or 3 times, and then you're only checking for the loop termination condition and doing some of that control logic once every 2 or 3 iterations of the loop, and that will reduce some of the overhead. It does a bunch of other things. It fuses loops together. It can turn more expensive instructions into cheaper ones, like doing a shift operation if you're multiplying by 2 and you've got an integer, things like that. So why do you need to worry about all this? Well, sometimes it will, as I said, do the best thing for the code and make these optimizations will make it faster. Sometimes you'll need to worry about it doing something suboptimal. And especially when you're doing performance programming, one of the examples that often comes up in the graduate parallel computing course is the students will unroll a loop manually. That is, they'll take the code and they'll just make copies of that and have the loop unrolled in the code, and that causes the compiler then to do other numbers of unrollings, and so you can have a difficult time getting exactly the unrolling that you would like in the code. So a better processor model then does take into account that these memory operations are much more expensive than the arithmetic operations. But when we start looking at memory accesses, we can really also divide the cost into 2 different pieces of the cost. The first is the latency, which is the cost to load or store a single word if you wait for the whole thing to happen. That is, you issue the load instruction, wait for the value to come back from memory, and that whole thing would be called the latency of a load. And similarly for a store, waiting for it to get written to memory. Bandwidth, on the other hand, is the average cost per byte of doing a load or store of a large chunk of memory. And so the cost per byte is going to be much less if you're doing a large chunk of data access, if you're moving a chunk of data, than if you're just moving an individual word. So this is one of the things you'll be looking at in homework 1, is how to measure the latency and the bandwidth from the software, so that you can get a sense of what the hardware bandwidth and the latencies look like. Just one more way of making sure we understand what bandwidth and latency are. I like this image from Katie Hempenius, and it is looking at, we can think about these as pipes, and the memory system, or the pipe between the memory and the processor, which is what we're trying to get data through, although we'll also use this when we talk about networks, for example, in parallel computers. And the throughput then is the bandwidth is the data throughput, the number of bytes you can get per second. And so a low bandwidth pipe is very narrow, and a high bandwidth one, of course, is very wide. Whereas the latency is really about the length of the pipe. And so we've got our low latency short piece of hose there versus a higher latency one. And so you can see that these are really two different ways and two different aspects of the performance, both of which can be very important. Historically, the gap between memory speeds and processor speeds have gotten worse over time. So it used to be that arithmetic operations were expensive relative to other things, or at least comparable cost. And now, because memory operations have become more expensive over time relative to the processor, the arithmetic operations, we need to worry about them a lot more. This is looking at the memory bandwidth gap, that is the cost in terms of the floating point operations that you can perform for any given memory access. So, and this is looking at bandwidth. So this is the bytes per second, or in this case, gigawords per second, and that is divided into the gigaflops per second. So, and you can see this on a log scale is getting worse over time. Now, even worse than the bandwidth has been the latency. The latency has always been substantially slower than the bandwidth cost per word or per byte, but and this has grown at a somewhat steeper slope, although they're comparable looking here. But certainly the gap is much worse, which you would expect, because the latency is really waiting for that round trip operation to complete for an individual word, whereas the other is really looking at the average cost for a byte within an aggregate move. So now we have our much more complicated memory hierarchy to deal with the memory and bandwidth limitations of these systems. And without going into details here, we can look at the relative costs of the different types of memory. So in addition to the arithmetic unit and the control unit on the processor, of course, we have the registers that we've already talked about. We'll also have on-chip cache. We may have some SRAM off-chip cache, as well as multiple, and may have multiple levels of that, in fact, as well as then the main memory, DRAM. We could have we could be writing out to either SSD or spinning disk sort of storage, and then tertiary storage, which used to be tapes, and actually at a supercomputing center like NERSC, you still have tape storage. There are robots that load and store those tapes, so you can imagine that can take several seconds. Actually, it's about, we're estimating here 10 seconds. So these numbers down here are not exact numbers. These are just sort of nominal numbers to point out that there's an order of magnitude or so between each of these levels of the memory hierarchy, more than a single order of magnitude when you go from main memory to secondary memory. But you can see that you go from, a single nanosecond, sort of a few nanoseconds, to tens, and then to hundreds, and then up to tens of milliseconds, and then going to tertiary storage is even another much more than an order of magnitude, several orders of magnitude here, or a few orders. But of course, then the size of the memory that you can access also goes up, and it goes from gigabytes up to petabytes when you get to tertiary storage and all the metrics and the numbers in between. So this memory hierarchy is designed to speed up the average case, which is great for average programmers when you're just trying to get pretty good performance out of any kind of complicated application. But if you're writing something like a library that's doing deep learning training, or you're looking at a library that's doing genome alignment for genomics, or you're looking at some other things, you really want to worry about the details of this, and you're going to want to optimize for it. So we'll look at that in the second homework assignment, and we'll talk more about this in the future lectures. So one other way to look at the difference between latency and bandwidth really combines them together by saying that how much concurrency do you need? How many things do you need to have in flight in order to mask the latency so that you run at bandwidth speed? Bandwidth is your fundamental limit. You can't get more water through that pipe than the bandwidth allows and the width of that pipe allows. What you don't want to do is be running at the speed of latency, which is the length of the pipe. You want that pipe to always be full. You don't want a little trickle of water going through just one kind of, or one word of memory at a time going out and back through your memory pipe. So there's a well-known law called Little's law that says that concurrency is equal to the latency times the bandwidth. And what that means is that if we, for example, if we've got a latency of 10 seconds, so this is not really a computer hardware number, but just to make the arithmetic and the units all easy here, and we've got a bandwidth of 2 bytes per second, so that if we invert that, we've got a half a second per byte. And so then we can pretty clearly see that we're going to need 20 of these operations going on at a time in order to saturate the bandwidth, that is to run at the 2 bytes per second relative to the latency. So this little picture gives you some sense of what that looks like. So if I've got my latency of 10 seconds here, each one of these are 10 seconds long, but if I issue 20 of them, then by the time the 21st is ready to be issued, the first one will have completed. And if you continue doing that in that sort of steady state, then you can, that says how many things you had to have that were done concurrently, is that those first 20. The 21st one can actually depend on the first one. So that's where, that's what we mean by those 20 things being concurrent. So that means that you're going to have to find 20 independent things to issue in order to saturate bandwidth, which will be one of the goals in performance programming. So just to wrap up, then I want to talk a little bit about class logistics, and we may do a little bit more of this next time. So first I want to encourage everybody to read the course overview, which is linked in the course website. And there's the course website and there's the overview piece of it. So there's my email address, and we only had 1 GSI for this class, so I'll ask you to be a little patient. We've got 80 students registered, and we've got a few more on the wait list. At this point, I expect probably all the people that were currently on the wait list as of the first day of lecture will get in, but others will not. So don't encourage all of your friends to come and sign up. We just do not have enough teaching resources to have more students in the class, and I'm afraid Ben will already be quite heavily worked. Sorry, to work on grading your assignments and running the sections and so on. There's a Piazza page. I think most of you have found that. The password for it is Parallel. And then just to summarize what the class meetings are going to look like, excuse me, the lectures are Monday and Wednesday, 9 to 10, not 9 to 10:30. The attendance is not required. It is optional, although I very much appreciate it if you're here to ask questions in person. And they will also be recorded and put online in B courses, so you can access them there. The labs are set up separately. They're not something that the registrar is actually managing, so you won't see it officially on your schedule. So we sent mail, and everybody should have gotten an assignment for one of the 2 lab sections. One of them is at 5 p.m. on Wednesday, and the other is at 1 p.m. on Thursday. If you haven't gotten mail, please email both of us to make sure that you do get assigned to a lab section. And you will also get assigned at that point to a homework group, and I'll say a little bit more about that in a minute. So the labs are 1 hour per week, so it's still a total of 3 hours per week that the registrar had you signed up for, but it'll be 2 hours of lecture and 1 hour of lab. We will have 4 quizzes that will be at 6 p.m. on Tuesdays, and those are the dates. So please mark your calendar now and let us know if you have any conflicts immediately with any of these dates. We are expecting that everybody, unless you let us know right away, that you'll be available for those quiz dates. And there will not be a final exam, and there will not be a final project. There will be weekly homework assignments that will include a combination of both written and, that is sort of, handwritten homework, as well as programming exercises and things to run and analyze and things like that. So we are trying to make the workload a little bit more uniform. I don't promise that all of the homework assignments will be easy. I think they may take you several hours, for a 4-unit class, which is what this is, you're expected to spend about 12 hours a week on in total work on this class. So, you know, about 9 hours of homework on average would be reasonable. Relative to what the workload is supposed to be, but just just expect that level. And the first homework is due on Monday, and it was handed out yesterday. It was on Piazza. Please, if you haven't seen it yet, please go and look for it on Piazza, and it will also be linked on the main website. The last thing I wanted to talk about is peer learning and academic integrity. And these two things really go together. So we are encouraging you, in part because we can't give you the sort of in-person social and educational experience that you would normally have when you're here on campus, and able to meet with your friends and others to talk about various things. I learned an enormous amount from my friends and colleagues as a graduate student and an undergraduate. And we want to give you that same opportunity to learn from others. And the other comment I'll make is that you will never learn something as well as you do if you are explaining it to another person. So if you feel like you understand something and somebody else does not, please take that as an opportunity to solidify your own understanding. Oftentimes people will ask you questions that you hadn't thought of and maybe reveal that your understanding of it maybe isn't quite as solid as it, or at least provide you with an interesting perspective on how other people may think about the problem. So we're assigning you to homework groups. That is, so you don't get to just sort of choose your homework groups based on who your friends are. This is partly to make sure that everybody is part of a homework group, that that nobody is left out of that experience, and also that we want to make sure that that's sort of consistent throughout the homework assignment, so that you all have people to share questions with and learn from. And that, by the way, goes for lecture. If you feel like you might have a question, but you feel like it's maybe it's silly to ask the question, ask your homework group first, and then come back with a question on Piazza or wherever if you feel like there's a more basic question that that none of your peers or the ones you ask can answer for you. So hopefully that will make it easier, and we'll get more questions that way. Now, does this mean that you should share solutions with each other as part of your homework group? Absolutely not. You are doing homeworks individually. They are not group homework assignments. And I just want to make that very clear. Each person is supposed to needs to turn in their own homework, and we're expecting you to adhere to that policy. The purpose of the homework group is to be able to discuss ideas. And just one clear rule of thumb is never share your code with another person, whether it's in your homework group or anybody else in the class, or for that matter, never make your code public so that some student in a future semester can find it in GitHub or someplace else. So we're really hoping that this will give you an opportunity for a new mode of learning, and that's available to everybody in the class. But you do need to then be conscientious and make sure that both, as somebody who may have figured out a solution more quickly than others, you need to think about ways in which you can help other people find the solution themselves, but not just give them the solution, because they won't learn it as nearly as well if somebody else just tells them what the answer is, and you won't learn as much by giving them your answer as if you actually try to come up with ways of explaining that to them, ways of thinking about the problem that might help them with their own insight into it. And as I said, there will be a combination of written assignments and programming assignments, but the rules follow for both. You should do your own work in each of those cases, and we are really expecting you to get more out of the class and think about how to get as much out of the class as possible by doing your own work. So with that, I think we'll end the first lecture, and we will see you all next week on lecture 2. Thanks a lot.